Hello friends, welcome to chemistry classes by Vijay Kumar Sethi, class 11th chemistry. We were discussing unit 7 equilibrium, and in this video we are going to discuss factors affecting equilibria, Lee-Chatelier's principle, and effect of concentration and pressure change on equilibrium. Factors affecting equilibria. These are the various factors which affect the equilibria: concentration, temperature, pressure, and catalyst. And the effect of these factors can be explained on the basis of Lee-Chatelier's principle. Now, what is its statement? It states that a change in any of the factors like concentration, temperature, or pressure that determine the equilibrium conditions of a system will cause the system to change in such a manner so as to reduce or to counteract the effect of the change. In a very simple way, we can say that if we change concentration, temperature, or pressure at equilibrium, then that reaction will shift, or we can say equilibrium will re-establish in such a way that effect of change is reduced. Okay. Now we will discuss the effect of concentration change. When the concentration of any of the reactants or products in a reaction at equilibrium is changed, the composition of the equilibrium mixture changes so as to minimize the effect of concentration changes. In a very simple way, we can say if we increase the concentration of reactants, then reaction will proceed in the forward direction to decrease the concentration of reactant. And if we increase the concentration of products, then reaction will go in the reverse direction to decrease the concentration of product as per Lee-Chatelier's principle. Okay, we'll discuss some examples. See, this is formation of Hi by H2 plus I2 gives 2Hi. Okay, if H2 is added to the reaction mixture at equilibrium, then the equilibrium of the reaction is disturbed. In order to restore it, the reaction proceeds in a direction wherein H2 is consumed. That is, more of H2 and I2 react to form Hi, and finally the equilibrium shift in right, that is in forward direction. Simply we can say we added one of the reactant. That's why reaction will go to decrease the concentration of reactant, and that's why this will go in the forward direction. With the help of one diagram, we can also represent this. This indicates the equilibrium where concentration of H2, I2 and Hi is constant. Now at this condition we added hydrogen. So as soon as we add the hydrogen, what will happen? This hydrogen react with the I2. So concentration of hydrogen is decreases, concentration of I2 is also decreases, but concentration of Hi will increase. Okay, and after some time again we will get the equilibrium condition. So equilibrium is re-established after certain time. Clear? Now, effect of concentration change with the help of reaction quotient we can also explain. The same point can be explained in terms of the reaction quotient, that is QC. For this reaction, if we write the expression of QC, then concentration of Hi square divided by concentration of H2 and I2. Now we have added H2. As soon as we increase the concentration of H2, magnitude of QC will decrease. Okay. Addition of hydrogen at equilibrium results in value of QC being less than Kc. And in the previous videos we have discussed, when QC is smaller than Kc, reaction will go in the forward direction. Yeah. Thus, in order to attain equilibrium, again reaction moves in the forward direction. Removal of a product also boosts the forward reaction and increases the concentration of the products. in case of manufacture of ammonia by the reaction of N2 and H2. Ammonia is liquefied and removed from the reaction mixture so that reaction keeps moving in forward direction and we will get more and more amount of ammonia. Let us see one more example. In the large scale production of CaO, calcium oxide, this is also known as the lime, and that is used as an important building material from limestone, calcium carbonate, and reaction can be represented like this. Calcium carbonate, which is solid, will convert into CaO solid and CO2 gas. If we want to obtain the more amount of lime, we have to remove carbon dioxide constantly. Okay, constant removal of carbon dioxide from the kiln, that is from furnace, drives the reaction to completion. That is one more interesting example, and actually this is a part of your practical, and we say this is the one cut without blood. Cut without blood. Okay, in this case this Fe3 plus ion is yellow in color, and when we add thiocyanate ion, that is this thiocyanate ion is obtained from the potassium thiocyanate KSCN, and that is colorless. When we mix both, we will get the deep red. Actually this color is similar to our blood red color we will get. And for this Kc, we can write this concentration of product divide by concentration of reactants. Okay. With the help of diagram, we can also represent this. This is the solution containing Fe3 plus ion, which is yellow in color. And as soon as we add the colorless thiocyanate ion, we will get the deep red color due to the formation of this complex ion FeSCN2 plus. Okay. Now this, once the equilibrium is reached, now see, the equilibrium can be shifted in opposite direction, that is in the reverse direction, by adding reagents that remove Fe3 plus ion or SCN minus ions. It means if we remove one of the reactants, reaction will proceed in the reverse direction to increase the more concentration of reactants. For example, oxalic acid, its formula is H2C2O4. When we add oxalic acid, it reacts with the Fe3 plus ions to form the stable complex ion FeC2O4 thrice 3 minus. And when this Fe3 plus ion react with the oxalic acid, it decreases the concentration of free Fe3 plus ions. So FeSCN2 plus dissociates to give Fe3 plus. And when this complex, which is in deep red color, when it dissociates, what happens on the intensity of red color? We can say when its concentration is decreases, the intensity of red color is also decreases. With the help of diagram, you can understand. This is our red color complex. When we add the oxalic acid reacts with the Fe3 plus ion, that is one of the reactant is decreased. That's why reaction will proceed in the reverse direction by dissociating this complex, so intensity of the red color is decreased. Addition of aqueous HgCl2 also decreases red color because Hg2 plus reacts with SCN minus ions to form stable complex ion, this HgSCN4 2 minus. Okay, this can also explain with the help of this diagram. This is the deep red color. When we add this HgCl2, again this HgCl2 is reacting with the one of the reactant, that is thiocyanate ion. When reactant is decreased, product will decompose to form more reactants. That's why this intensity of the red color is decreased. Removal of free SCN minus ion shifts the equilibrium from right to left, replenish SCN minus ions. Okay, like this. Addition of potassium thiocyanate. Now we are adding one of the reactants. So in which direction reaction will go? When we are adding the reactant, according to the Chatelier principle, reaction will go in that direction, will decrease the concentration of thiocyanate ion. So reaction will go in the forward direction. So there is an increase in the intensity of red color. Okay, because solution shifts equilibrium to right side. This can be explained with the help of this diagram. This is our red color. When we add the more amount of potassium thiocyanate, there is more amount of this red color compound is formed.
So intensity of the red color is increases. Now effect of pressure change. Effect of pressure changes on solids and liquids can be ignored because the volume and concentration of a solution or liquid is nearly independent of pressure. Effect of pressure change is observed where gases are involved. Okay, so gases are involved and total number of moles of gaseous reactants and total number of moles of gaseous products are different. Again remember, if there are same number of gaseous moles of reactants and products, there is no effect of pressure change. Okay, see one example. CO gas plus 3H2 gas converting into CH4 gas plus H2O gas. Here 4 mole of gaseous reactants. How 4? 1 mole of CO and 3 mole of H2 becomes 2 mole of gaseous products, that is 1 mole of CH4 and 1 mole of H2. When pressure is increased, number of gaseous moles increases per unit volume. So the reaction goes in the forward direction because the number of moles of gas decreases in the forward direction. Okay. On increasing total pressure, the partial pressure and the concentrations are increased. Okay, that's why we can find out the QC. When we increase the pressure, total pressure we are increasing, so partial pressure will increase. In that case, when partial pressure is increased, the denominator will increase. So QC becomes less than KC. Okay. As QC is less than Kc, the reaction proceeds in the forward direction. See one more example. C plus CO2 converting into 2CO. Now see, in the reactant side there is only the one gaseous mole. In the product side there are two gaseous moles. So what will happen if we increase the pressure? When pressure is increased, the reaction goes in the reverse direction because the number of moles of gas increases in the forward direction while number of moles of gas decreases in reverse direction. Okay, we can make one generalization. On increasing pressure, reaction will go in that direction where number of moles of gas are less. Clear? Number of moles of gas are less. Okay. Thank you. Subscribe my channel to get the next video from this chapter.